Welcome everybody to my talk about reverse engineering for CTFs 101. There will be some assembly required today. About me, you can reach me on Twitter at Savino Jossi or email at sj@lodge.org. I'm also part of a beautiful CTF team, the Que Pasa Zombies. We often place second in CTFs and sometimes lower. And since I'm the go-to reversing guy and I'm usually the one that gets shoved all the executables once people are stuck, I want to share my knowledge a bit with you a bit, and so that everybody can also take part in the joy of reverse engineering binaries. Just a quick thing, I have Discord and all the chats disabled, so if any questions come up, I'll look in the chats at the end or probably get pitched during the Q&A session, so we'll keep the questions for after. So in general, what do we expect today? We expect we talk about Linux binaries, reversing of Linux binaries. There will be, because the CTF challenges are also Linux binaries. I didn't want to confuse you with any Windows peculiarities or anything else. And there will be no binary exploitation. So there will be no stack overflows, no ROP chains or anything of those likes. I'm just trying to give out the tools to give you an idea of how to approach a reversing challenge. When you look at a binary, what can you look at? What do you look at? What do you look for? And this will also then give you the tools to learn binary exploitation, because you will have to understand the binary before you can start abusing it. Now, the roadmap of the presentation is a quick intro to assembly. Was supposed to be quick, now it's a pretty big part, but I felt like I wanted to really lay out the groundwork so everybody feels comfortable looking at assembly instructions, understanding them, and trying to take away a bit of the fear of looking at them, because if you first see the mnemonics, they seem pretty scary, but once you get the hang of it, it's kind of intuitive. We will talk about static analysis of the binaries. So when you first receive them, you don't want to run them yet, because who knows what they do on your computer. And then the dynamic analysis when we run them and see how they behave during runtime. Now, to clear up some misconceptions I often heard when I start to talk about reversing, how cool reversing is that there's a feeling that assembly language is hard. And well, yes, it is hard, but no, not really. The issue with assembly is that it's there's basically no abstraction. So writing an if, else, or for loop or something along those lines will take considerably more instructions, because there's no abstraction to it. And even worse than reading assembly language is writing assembly language, because you have to use the right instruction for the right situation that you're using. The cool thing about reading it or reversing is that you often don't have to write assembly, so the right instructions are already in place, so you just look up what it does, and it should be fairly obvious. The second one is that I'm not a coder. How do I reverse binaries? And as I said before, assembly is very lacks all these abstractions. So what you do when you read assembly, it's kind of like a cooking recipe. We'll see with the instructions that we see, they're extremely simple. There are no complex, I don't know, function overloads or any complex concepts to assembly language. It's basically just put this here, do this there, and if this is here, then maybe jump somewhere else. So there's no coding skills required. Just read up on what the instructions do. To get some kind of understanding what an assembly instruction does is it's an instruction to the actual CPU, the bare bones CPU, in a readable form. So we'll see the move EAX at the bottom is what you read, and there's actually on disk or then loaded into memory, loaded into the CPU, and then executed by a CPU, a bunch of bytes. These are plain old binary bytes. You can look at them in binary, which is not so fun. You can look at them in hex. You'll get a hang for a few instructions in hex, or you'll see those mnemonics. The mnemonics are fairly short, but I think once we're done with the assembly part, they should make a lot more sense than they do now. Because the instructions are made for a CPU, they are CPU dependent. So if you're, for example, on a x86 Intel platform, you will have different instructions that behave differently than, say, on ARM, MIPS, RISC-V, what have you, all the processor platforms that actually exist. And there will be differences to the instructions in general. Now, Intel x86 is what we call a CISC, a complete instruction set. It tries to have an instruction for every single thing that you want to do. So if you want to multiply something, you can just tell the CPU to multiply something here in a register with the immediate value. We'll talk about that later. The ARM, for example, is a reduced instruction set platform. So to do this one step in ARM, you have to do probably 4, because you have to load it somewhere, and then you have to do something with it, and then you have to store it somewhere else, which reduces the complexity of the processor somewhat, but it increases complexity for the people writing assembly. Luckily, since we don't write that much assembly manually, it's not that much of an issue nowadays. Also, the registers that we talk about today, they will have different names and definitely different uses on other platforms. So for every platform, you have to get used to the environment. You'll have different numbers of registers for different CPUs, even on the same platform. Now, this is important when buying disassemblers. I say this because the fairly popular interactive disassembler IDA, depending on the version you get, is the license is for one specific platform. So if you buy it for Intel, you can't do ARM. If you switch between platforms a lot, that is kind of important. If you use one of the flexible licenses or one of the open source ones, you won't have these issues. But you still have to watch or look out for which platform you're using. As I said, today we're using Intel because we have Linux binaries that are run on Intel. And one word for the syntax. When you first open a disassembler, you might be greeted with either of these syntaxes. Now I say syntax because these two instructions do the same thing. It's just that AT&T, which is a bit, the AT&T syntax is a bit older. It came from the Unix times in the 70s, and GDB, I think by default uses AT&T syntax. And then Intel said, well, it's a bit too complicated, we'll clean it up. But let's see, my bad. They do this exact same thing. They just the things are the instructions are displayed a bit differently. I'll explain the differences to you, so we can then pick one and stick with it. Intel and AT&T have the biggest difference, and that might trip some people over at the beginning. It sure did me. Tripped me over. Was that the Intel assigns from right to left, and the AT&T assigns from left to right. So if you write, say, a 4 to the register ESP, then you have the value that goes into the register on the right side, and AT&T does it from left to right. Now, when you say it out loud, it's harder to say add 4 into ESP or add into ESP4. It's a bit confusing. But if you use a programming language, you have the variable on the left side and the value on the right side. So also to me now Intel feels much more natural. But pick the one you like. I'll just pick. We'll just pick one for this talk so we can always see the same syntax. Now, AT&T also has these sigils, they're called. It's much more verbose. It will tell you the size of the operation. After the L, it's a long value. It will declare the 4 as an immediate value with a $sign, and it will show you that ESP is a register with a percentage sign. The reason why we don't need to display this is that ESP is not an immediate value. So I don't need to see that ESP is a register. I just see it from the name. 4 is also the immediate value. There's no register 4. And if the value has a certain size, it's already implied which size it is, so we don't need the description of the long. So we can just do away with these and be able to read it much more cleanly. That's why we choose Intel. It's much less bulk, and I could fit more characters onto the slides. So that was also good. Now, if we talk about Intel assembly, we touched upon it before. We will talk about registers. Registers are temporary storage on the CPU. It's the fastest storage that you have. It's around 100 times faster than RAM. So it's always good if you can use registers in your programming. The problem is they're really small. So on a 64-bit platform, you have a 64-bit register. They will start with R. In most cases, I try to stick with R. You will see them starting with E also, and that's just different. That's the different lengths of the registers. So on 32-bit, it was EAX, EBX, and ECX. On a modern CPU, you mostly use RAX, RBX, RCX, and R8 and R9 are only on 64-bit. They have different name per platform, as I said, and they have different sizes. Now, these are general purpose registers. They had some meaning in the past, but in general, if you're writing assembly, you can just dump something into it, and they have no special meaning except to hold temporary storage. We do, in fact, have a few specific registers that have some meaning. Most importantly, the instruction pointer, which will point at the instruction that will be executed. If you mess with this, you can directly mess with the instruction of the CPU, with the instruction flow of your program, but it's something that you often don't want to do. We do not touch upon these today because there's no exploitation involved. I just wanted to show you that there's also a few specific registers. I also have to talk a bit about endianness because we work on a little endian system today. It's kind of the same way as we talk about numbers. Now in binary format, you have the last digit is let's see, so the pointer here. That should work. I hope everything works. Someone yell at me if I broke everything now. The last digit here is a 0, and that's 1 times 0. Then the second digit in the decimal system is 8 times 10 and 2 times 100. So it should be fairly obvious. In binary, it's 0 times 1. It's always exponentials of 2. So we have 1 times 2, 1 times 4. Now little endian just says at the end is the littlest number. And if we have a big endian system, we have the biggest number. If you just have to get used to it, especially if you switch platforms to something like MIPS Big Endian. You'll first get thrown off because you're so used to seeing your numbers one way. But I just wanted to point out that we're using little endian today. So to talk a bit about assembly instructions, I'll start out with the basic operations, arithmetic operations specifically. They should be fairly obvious to read also. The nice thing is that they're just really short mnemonics for what they actually do. So if you want to add a number to something, we can say we want to add 12. And remember, Intel assigns from right to left. We add 12 to the value that is stored in REX. And the same thing happens with subtraction, where you can subtract the value 12 from, for example, RBX. You can also do this with 2 registers. Then you subtract the value that is in this register here from this register there. You can also do it with 2 numbers, but there's nowhere to save it. So except for some corner cases, you won't really see this. For those familiar with logical operations, I'm not going to go into it because we don't need them today for the challenges. But let me unplug my keyboard. It's just getting in the way. We have some logical operations also. This is just 2 examples. We can do an AND operation on a register or an XOR operation on a register. There's obviously also normal ORs, there's negative ORs, etc. So we have all the logical operations also. Now, one of the instructions you will see a lot is the move instruction. That's to move data, say a value, around from one register to another, or you can move a value directly into a register. This will be you will see this a lot in the binary listings because computers mostly just shove numbers around in general. And, especially on say ARM platforms with reduced sets, you will have to move something into a place, then add it. So it will be much more prevalent there. But we'll see it today also. Now here's a slide. It's the most complicated slide we'll see for now. We will see it in the disassembly of the 2 challenges in the CTF, so I wanted to touch upon it. So you're not totally confused when it shows up. You don't need to you don't need to be able to explain it if you didn't see it before, but just so you have an idea of what it does. It's you can operate on an address that is stored because registers are really small. You can't store huge values in there. Anything greater than 64-bit is basically not possible, at least on Intel 64-bit. So if you have a larger number, or say you have a string somewhere, you can have a register point to that address, point to some location in memory and say, here's something I stored. And we have operations that we can actually work on these 2 by using these brackets. We operate on the value that is stored on the address. Did I break the presentation again? Great, my sacrifice to the demo gods didn't work. So we operate on the value that is stored in the address. So for example, REX points at 1004. Then we can add 4 to that value that is stored at this address. You see it here, change from the 4 and add 4 to it, and have an 8 in there. So you will see the syntax. It won't be required shouldn't be required in the challenges today, but if you come across it, you should at least know what it's about. Now, after operating on all these addresses and values, we start moving around. We can control the instruction flow, kind of like if this, then go to, except go tos are bad and jumps are totally fine. We can just plain jump to an address. We can say jump to address XYZ in memory, and the next instruction that will be executed will be the one at this address, and it will continue from there. Now, this is not as exciting as being able to do an if statement. Now, assembly has an if statement, but it's already complex, a bit more complicated to even what to check for. So you will have to compare two values and then act on the result. So if RAX, for example, it contains 4, then you can compare RAX to 4. And if the values are equal, you jump to this address. You can, of course, check if RAX does not contain 4 and jump to this address or another address. You can also do more complex comparisons like jump if less than 4 or jump if less or equal than 4. There's some trickery behind it that we can get into if we have enough time at the end. But this is everything you need to see. You need to know for now, because this is something you will definitely see. There's a lot of flow control in binaries, and of course, if greater than. And there's many more. The list is very it's basically endless. If you look at the Intel documentation, you have a beautiful book to read just before going to bed. It's only 7,500 pages, and it will put you to bed. But if you look it up as a reference, it's very useful. Jump if greater or equal to. Right. So something that you're maybe used to from higher level languages is calling a function. Now in assembly, you can also structure your code into functions, and the control flow will go into a different section, the section where this function is. Go into it, execute everything, and then return back into the function it was in before. Kind of like calling a function from Python, C. Then you go into the function, you do something, and then you return. Because this is assembly, everything is a bit more verbose and more complicated, but the concepts are exactly the same. Now, what I can tell you is what to look for and what to ignore. At the beginning of every single function, you will see the function prologue. It has about 3 lines, and it does some shuffling with the special registers I talked about before. You can ignore these. Just for now, they have no function that's that there's nothing that you have to do with this information. Just know it's there. It sets up some of the memory and then starts execution. And at the end, it undoes all this. Now, we have one single instruction here that's called leave. It's the equivalent, it's the inverse of this action. There's actually a prologue that is called start, but you won't see start for crazy reasons, as many things in reverse engineering. There's just a random reason why you won't see start. And so we'll see this instead of start, but basically see this as the start part. You can also see this written out, but for some reason leave is totally fine, whereas start is not fine. So we'll see leave in red. Now red will return to the function that called us. Now we jumped into function foo here, and say we're in the main function we call foo. Does a prologue, does some addition and some moving around, some jumping anywhere, and then at the end it leaves. Undoes all the things in the beginning and then returns to the instruction flow to main. This is something you'll see at the end. You won't have to do anything with it today. And this is it for assembly. Let me check the chat real quick if everybody's overwhelmed now, because I talk quicker than I thought. No, I think you guys are hanging on pretty well. If you have questions, write them down. I will get to them later at the end of the session, and we can answer them there. Also, I will be in the CTF, probably voice chat. Also, I will be coaching a bit the reversing challenges for the CTF. Should be fun. I'm excited. Now, To the static analysis, this is not directly a static analysis of the binary, but it's one of the most important CTF hints I can give you is to read the question. Please read the question. If you get stuck, read it again. If you get stuck later on and think you have the answer and you don't find the flag, read it again. Oftentimes, it either gives out the technique you will have to use, or the trick they use to hide the flag, or if there's, I don't know, some misdirection or something. The questions, or even the question title, are really meaningful, and CTF creators usually put a lot of thought into it. I hope, at least that's what I expect from them. And kind of in line with that, also not looking at the binary, depending on the rules of the CTF and your taste for winning, take as many hints as you want. We do on the CTF, so we do. Sometimes the hints are tiebreakers. If we see a chance of them becoming a tiebreaker, we might go easy on hints. In other cases, we just unlock all the hints to get all the information, because if time is an earlier tiebreaker than hints, you want to be faster. And if the number of hints don't matter, then you're faster with the hints. So take them. If you're not as competitive, you don't want to necessarily win, then the hints often also have background information. So instead of just finding flags by luck and then being done with it, the hints usually teach you something, tell you something, you might be able to read up on something, and the hints are generally really valuable. Also, sometimes go back to the challenges and read the hints again after you solved it to kind of understand what the hints meant. And maybe you missed something, maybe you skipped something. You can go to the CTF creator and say, I don't think you meant it to be that way, and it'll be a very interesting exchange. Now, for the actual analysis of the binary, the first thing I do, and a thing that many experienced CTF players do, even if they're not reversing, they just run strings on it. And strings, if you haven't heard of it, is this wonderful tool that takes the binary and basically finds anything that has readable characters, at least 4 if you leave it on default, and then is null terminated, which is in a binary what you would expect a string to be. You have readable characters and then a null byte at the end to say this is the end of the string. It will dump everything. Sometimes you might find a flag in there if it's not hidden well. If the CTF creator missed this, they often won't, especially at more complex levels. But in general, just run strings on it. We'll tell you other information like functions used. This binary uses printf and malloc. You will see debugging symbols sometimes. This looks oddly like a format string for a printf, so maybe that is something of interest. There's a lot of stuff in there. For reverse a firmware image, you might see copyrights, you might see references to GitHub repos, you might see pages and pages of GPL license information, which is extremely exciting to read. It's just always a good idea to just dump the strings and just scroll through them. Sometimes you pick up something that you would have missed otherwise. Now, something that isn't as raw are symbols. Symbols are in embedded information in binaries. They're usually used they're usually debugging symbols, so they have function names. So when you debug the binary, you can open up your source code and it will link the source code to the binary. It could have variable names. There's a lot more information. In easier challenges, the symbols are usually left in there because taking away symbols just makes it harder to read functions, but not impossible. So taking them away will make you use much more time, but they usually won't take away any important information, except if there's a function called here's the flag, or this is the very important function you have to look at. Then you save a lot of time, but it's nothing that's taking away symbols usually doesn't make it harder for reverse engineering, as opposed to techniques like obfuscation or similar things. So I took a semi-random binary and dumped all the symbols, and we can see some internal links to libraries in the libc. That's the Linux general use library for most of the stuff you want, say printing, allocating memory, opening a process, opening file handles, etc. Everything is in the libc. A binary will tell you that it uses printf from the libc, so we probably have some output. Then we have a function called foo, which does something, and a function called print. This is not printf, but it's actually a separate function called print. This is something that might be worth looking at. We see some memory allocations. This is just some information. The more you get used to reversing, the more you can kind of pick out the interesting symbols. Instead of dumping it with object dump on the command line, your disassembler will usually show you the symbols and extract and categorize them. So you only have the function names. This is an IDA output. You only have a, excuse me. So you'll see the main function that was declared. This is highlighted. Apologies, I'm talking too much. I should let you hack more. We have the main function that's highlighted, probably because I'm in it. And there's a foo function, there's a print function. We see references to other functions. These are external, these are not in the binary, but just referenced, so you can get an idea of what is used. This is still the same information as what we had here, just in a nice overview. Same in Binary Ninja and Radar 2. Now, especially for CTF challenges, this is kind of the point where we go from CTF to real-life reversing. The main function in huge binaries, like your regular application that you're running, won't do much except call other things. So the main function might not be the most, say, efficient way to start something. In a CTF where the code is much more compact and much more focused around the one thing you have to reverse, the main function is not even a bad idea to start out with. Sometimes it will just call the one CTF function, but this is then already the one you have to reverse, analyze, look at what it does. It might directly call the key generator or the flag generator, as opposed to a real application where the license check is hidden somewhere in a sub module, which you'll have to find first. Again, for any application, you will find it. It will just take much more time. Now, looking at this random binary from before again, we use GDB here because it has text output and the commands are fairly readable. So we can look at a little part in the function main, and just look at if we see if we recognize a few of the instructions that we have, and already see some of the information we also gleaned before. And GDB, I will have a cheat sheet up in the GitHub that I posted. The slides are also there. It's in the slides and links channel. We'll have some all three GDB commands that I know and use, so you can also use them. So we can disassemble the main function, and there's a lot of other things that we don't care about for now, and we just look at this little snippet here. We do see a jump if greater than this value. There will be a compare before, but since we don't know what will be in the register, this is information that we don't even look at yet. This is static, this is not moving. We don't know we mostly don't know what it will be when we look at it live. And it will jump somewhere. at some point. And here's a call. Like I said, it's a function call to a function print. We saw this in the symbols before. And we have a function call to foo. If you look at the details, and GDB will tell you, it jumps to plus main plus 40. And this is just offset in the function, which is right here. And if this certain condition is met, then we jump here, and the next step would be to move the value 0 into the register EAX, and then call the function foo. That's it. That's all we need to know. That's how I start out and just see, do I see function calls? Do I see checks? Does it skip calls in certain conditions? And can we match those conditions? Can we actually change the program flow? Say if it has interactive input, has standard in input. If we give it the right input, does it change the flow and go to this function? But this is just generally a pattern that we see. Do we skip the print function or no? Now another very interesting function calls that I always look for are printfs. The printf call is, as I kind of touched upon before, is in the glibc. It's a regular print to the console function. There's safer versions like sprintf, but nobody uses them because safe is lame. Don't listen to me. Printfs are usually the text that gets printed to the screen. Oftentimes the flag will be printed on the screen. So just looking for all the calls of printf and understanding how we get there might actually get you to the flag if you already identified the uwin condition, the uwin function, and you just need to find the conditions to get there. So printf in your disassembler, find all the instances of it and go look how you get to them or see what they print. Something very CTF specific. I say this because any compiler with half a brain will not include functions that are not called. They're just garbage that is never used, and they should not exist in a binary. Sometimes edge conditions, they may arise, but if you see an uncalled function, especially in a small binary, they're very often an exploitation challenge where you do, for example, a function pointer override, but this is something that you can skip if it's a harder challenge. If it's a remote challenge, you actually have to do the binary exploitation. Or in some cases, you can do some binary patching and see if it does something useful. We'll get to that later, though. Now, dynamic analysis is more or less running it and seeing what it does and try and see what actually happens when it does run. If we take our mystery binary from before, we'll do a segmentation fault. Doesn't print anything. The segmentation fault means that it tried to access memory it wasn't supposed to, and Linux will tell it to never do that again and kills it immediately. So this is a program that doesn't do much, and it probably doesn't do what it was supposed to do. We never get to, we never probably don't reach a print function. We don't see any output before it gets killed. So how do we find out what happens? We can use GDB for its actual purpose, which is being the new debugger, and run it in GDB. I again have this in the cheat sheet. We load the binary. It does read the symbols from the binary, and then we start the binary. This doesn't run it, but loads it into all into the memory segments that are that it needs to be in. So anytime we operate on something, it's already in the right place. If you don't start before you start setting breakpoints or something, you might run into memory access issues. So usually the first thing I do is I start the binary so it's loaded into memory. To quickly show you the difference is if you load the binary, I loaded it here, I disassemble it, the memory addresses are in the 1000s. If I then start it and it gives me some more output that couldn't fit on the screen, disassemble it again, we see that it's in the 800,000s, 8 millions. This, if we had set a breakpoint here, it wouldn't be the right breakpoint again. It wouldn't be the right breakpoint anymore, and we couldn't actually debug the function the way we wanted to. So just start it first, it's a no-brainer. We can then continue the execution and let it run, basically. We continue execution and we see that it gets the segmentation fault that we saw before, but now we actually have some possibilities to look at what actually broke. So when we disassemble without telling it where to disassemble, we see the disassembly for where the instruction pointer is. That means this address here was an illegal instruction. Now what I do is I don't even try to, or I kind of try to clean something around it, but this doesn't make any sense to me at first glance. So at a CTF, I usually just try to move away and look around it and see if there's another path that I can take, or if there's something else that makes sense at first glance, because debugging every single of these instructions is tedious and usually not what the CTF challenge is about. So we see it breaks here, we know where it breaks, we don't really know why it breaks. So let's go back, and I missed something. I didn't highlight it, that's why I forgot it too. We see that we're in function foo, actually. So when we look at the disassembly from before, we are in function foo. We didn't see any print, anything printed to the console. So let's assume print was not called because this condition was met. We can actually prove this fact that a print wasn't run, but I'll leave this as an exercise to you, or we can talk about it in the CTF chat. I'm running low on time already. So let's look at the condition here. It checks if, and that's why I had to show you the brackets before, if whatever is in this register at the address that this register points to, it checks if it's 0. If it's greater than 0, we jump to foo, and if not, then it would call print here. Since we're running it dynamically, we can actually take this address here, the 11.5b, and set a breakpoint on it. So in GDB, we have to use prefixes for an address, but they're not the same as AT&T syntax, so it's even nicer. So we break at this address. I usually copy paste, that's why I have leading zeros. And you can shorten commands down in GDB. At some point, you will just use 1, 2, 3 character character commands, because typing disassemble is super annoying. And you can ignore the leading zeros also. We can then continue, dump the information, see what the check actually does, and we confirm that the compare here is, the value here is greater. It jumps over here and it calls foo. We don't want that. We want to print. We want to actually see what the program wants to print us. Wants to print so we can see what it does. We want to reach this call here. So what we can do is you use this with a /R. If you're in a different disassembler, it might actually show you the instructions. This here is exactly the same as what I showed you in the beginning in binary, just represented in hex. This is the binary representation of this instruction here. This is important because jump if greater than might have a few different versions, and we want to find the right version. If you look at the documentation, it might makes a bit more sense. So we go into the documentation and look for 7F. 7F was the first byte here. Look at 7F, and it tells me it does jump if greater than on. I don't care right now, and we kind of want to change that. We want to actually do the opposite. So instead of when it's greater than, we want to jump if it's less or equal than. So it covers the opposite case. And we see that this is 7E and whatever byte comes after. The byte that comes after is usually the offset that it specifies, but we don't even need to think that far because 7F is greater, 7E is smaller, is lower. Let's do it. We can open the binary in you can open the binary in your favorite hex editor. I'll be around. I'll show you some hex editors. I'll give you some references in the end. And the CTF coaching team will also help you do that. But just to show you real quick, I opened it in a hex editor, find the 7F0C that we saw before, change it to a 7E, and save it right to disk. If we load it, we do actually see that GDB sees the 7E and sees that it's a jump if less or equal than. And we just change the instruction flow and actually do reach the print function that might or might not be interesting. And that is one of the techniques you can use if you're in a local challenge. If you're in a remote challenge, so you connect to a server, but you get the binary, you can change the binary, but you have to do some remote exploitation. This usually has to do with the input, is some binary exploitation, and as I said before, we're not covering this today. We're almost at time too. But this should give you an idea of how to read the binaries and some tools to actually deal with instruction, deal with conditions, and get a general sense of what to do. Now, experience is then the secret sauce of actual reversing. And as I said before, we just run strings first. It's usually helpful. You find some information, and oftentimes it drops the flag much earlier than the creator wanted. Part of the experience is also that that it's a huge field. As I said before, there's a lot of instruction sets, there's CPUs. The binaries differ from Linux to Windows. There's different call behaviors, there's different kernel calls, there's many different parts to each of these fields. So at some point you might do a lot of Linux on Intel. If you look at a hardware device, IoT hacking, you will look at very interesting CPU platforms. ARM is very popular there. You will see some MIPS. I don't think PowerPC goes that small, but you will see PowerPC, the old Apple devices. Maybe you want to get into malware reverse engineering, which is a whole different beast. It will try to obfuscate. It will try to do something but show you something else. There's tricks against the disassemblers. There's unpackers and packers and crypto stuff. Or you want to get into exploitation. So you just reverse the binary and see where the fault is, and then try to exploit it so you can take over the instruction pointer and the memory and everything. Yeah, by now this joke seems old, but I'm not the only one who thinks that grabbing for flags is fun. So this is something you can actually do, and without having to look for through the strings output, you just dump the flag, and sometimes it's in a one-liner and you get the point. Now, just a quick list. These are the tools that I've used before, except for the Mac one, because I haven't had a Mac in a while. HXD is a very nice freeware, but not open source hex editor for Windows. UltraEdit, if you have a license, is obviously very powerful. dhex and is a CLI hex editor, and Radar 2 is a disassembler, exploitation helper, everything do it yourself, but it's I like to use it for hex editing too. And then if I get into disassembling, GDB does disassembly. It gets cumbersome when you do more complex disassembly, but for starters, it's on every Linux machine or most of most base installs. GDB is somewhere. You can get it very easily. EDB, I was told, is a nice interface. It's a graphical interface where you can use your mouse and click. I haven't had much success with it in the past, but other people used it successfully, so give it a shot. Radar, I still don't know how to pronounce it. Please correct me. It's a very powerful framework, but very CLI based. Cutter is a GUI on top of Radar that is very powerful. I haven't played around with it, but it looks very, very nice. IDA is kind of the industry standard and can be free up to very expensive. Binary Ninja is a cheaper alternative. They have a nice trial that lets you disassemble for around 25 minutes, which from my sessions was sometimes too short, but for the CTFs it should be good. I hear good things about it too, and Hopper is also here. I haven't tried it myself. Now we have 10 minutes left. I'm asking the moderator if we should go for a deep dive or go to Q&A. Do we have a lot of questions?
So I'm looking through the Discord, and I've been watching our GoToWebinar questions thing, and really the chat is doing really well at answering questions for each other.
Awesome.
Yeah, talking about a bunch of different tools that could be used, and oh, somebody's wondering why you didn't mention Gahidra. Did I say that right?
Oh, Ghidra, I forgot Ghidra.
Yeah.
Yes, Ghidra also exists. It's very powerful. It has some features that were previously not available for free. I didn't like it because it was on Java. It didn't really work with my Linux setup. So, but definitely try out Ghidra. It's very powerful.
Awesome. Yeah, I mean, let's see. I don't see any other questions coming in at this time. So, oh, okay. Hold on. Let's see. Here's a good one. What's the hardest flag you've ever encountered?
The hardest? What?
The hardest flag you've ever encountered during a CTF?
Oh, it's still unsolved actually. At the Metasploit CTF recently, I got a RISC-V binary, and it did have some more complex binary exploitation in it. So you would have to do some RUP. I think it was a few RUP chains. I looked at the write-up, but I didn't want to spoil it too much. And I didn't know the platform at all. RISC-V is it's basically, instead of coming from a commercial sector like Intel and ARM that just built their processors and built their instruction sets around it, RISC-V was a academic exercise. And people actually started building CPUs with it. They have super low power CPUs now. They have massively parallelized CPUs, and the instruction set is very, very interesting. It's very cool, and I'm very excited to try more. But that's a flag that I still haven't cracked yet.
Awesome. Another good question is, what is the most newbie-friendly tool to start with, or are they all difficult for doing this?
For the challenge today, I used Binary Ninja, and if you don't run into the time limit, it has the least windows, so it's very focused. You should be able to reverse the binary, and it does hex editing too. So the screenshots from the hex editing was from Binary Ninja. Since you don't, you can just, after the trial ended, you can just restart it, and you will lose all the information you got in between, but it's basically just an attention span breaker at this point. So I would probably recommend Binary Ninja. It's also multi-platform.
Awesome. See if there's anything else in the Discord popping up. I guess a question I have, just what's a good resource that people can go to learn more about this, whether it be a book or a YouTube page, anything? Where can people learn more?
It depends on what you want to do. That's kind of the problem. I will put some resources in the GitHub page. I will have a markdown cheat sheet with some resources. But for say binary exploitation, The Art of Exploitation, it's a fairly old book, but it's very good on beginners, or like back then the really new techniques on Stack Overflows and everything. And this will force you to read a lot of assembly, understand the Linux platform a bit better. And it's a very good read for that's how I got the most practice in reversing, actually. For the malware stuff, I think there's the malware analyst hand. I'll put it in resources, but there's malware focus books, there's more binary exploitation focus books, there's Windows books.
Yeah, +1 for the art of hacking, but that's how I learned. I mean, it was very helpful. I highly recommend it to anybody. It's often on sale on Humble Bundle, and highly recommend it. Let's see. I'm not seeing. We have some people typing, so we might have some more questions coming in.
Let me see if I have a fun deep dive slide here somewhere. No, while the typing, I can maybe go into the JLE issue if you have a minute. Why did we choose jump if less or equal then instead of jump or instead of something else? And I was asked that yesterday during the demo run. I'm lazy. What some people for sure heard about is, or what you use in other situations also, is a NOP instruction, and that it's just it's 1 byte. The problem is you have to count the bytes that you have to override. So instead of just knopping out this, you would have a stray byte. So you have to nop out 2 bytes, or in this case, it's 5 bytes, and you have to count. But I'm lazy, so I just invert the instruction, and then we're done. Also, it's really close in the documentation, so I don't have to think, and laziness is faster, and CTFs, that's all that counts.
Yeah. Let me see. If not, we might. How often do you script in binary CTFs? Do you find most flags just from disassemblers?
No, oftentimes you have to run the binary, and because copy pasting the same input will be annoying, I usually script something. If it's easy, I do a shell, some bash or some piping or something. If it's more complex, or if I need special characters, if I need 500 A's all of a sudden, for whatever reason, I usually use Python, and I often use the Pwn tools library. They were finally updated to Python 3, and I often use Pwn tools because it's just much faster to explore.
Awesome. All right, I'm going to bring in our next speakers, but I thank you so much. And you said you'll be in the Discord helping with the CTF?
Definitely. I'll be in the Discord. My friends from the zombies will be in the Discord. JMPOC and Nemesis will be there. And little shout out to Jossi and Kuhn without Twitter still. We haven't convinced him yet. Just for being awesome. Thanks for helping out. I have some more shout outs for people that help me, for people that have great resources. And thank you guys for setting everything up.